Welcome back to Bio 6612. In this lecture, we'll cover modeling count data using Poisson regression and the details of the Poisson regression model. So this slide comes from the previous lecture, and the Poisson model is the most frequently used model for count data, where the setup I indexes either subjects or cells, depending on how your data is set up, and this is analogous to having group level or individual level data, like we did for logistic regression. Yi is the event count for the ith subject or cell. Xi is the covariate vector for that subject or cell, and Ti is the exposure for the ith subject or cell. When you're using Poisson regression, we're assuming a Poisson distribution for our data. And the PMF of the Poisson distribution is given here, where y is your random variable or your outcome, and it's modeled with the parameter lambda, which is the parameter for the rate. And so the expectation of y when you have a Poisson distribution is lambda, and the variance of y is also lambda. So in this case of the Poisson distribution, the variance is equal to the expectation. So we can use the GLM framework that we've been working with, where you have some length g of the expectation of y given x equals x transpose times beta to model the relationship between the outcome and covariates for count data. And in this GLM framework, for Poisson regression, the data distribution we assume is a Poisson distribution, and the link function g is the log link. So in the GLM framework in general, our link function g maps the expectation of y given the set of covariates x to the linear predictor, which is x transpose beta. So for linear regression, you have the identity link, which is g of whatever, let's say z equals z. That gives the model expectation of y given x equals xi transpose beta. For logistic regression, we used the logit link g, which gives the model logit, and then the expectation is of y for binary data is the probability, so that gives the logit of the probability equals x transpose beta. Or if you, which is equivalent to that statement here, if you just take the inverse logit and look at the probability equals the inverse logit of x transpose beta. And then for Poisson regression, we have g is equal to the log, which gives log of the expectation of y given x equals x transpose beta. Or you can view that equivalently as looking at by exponentiating both sides to get the term that's written here. And I have it written two ways. I have this first one here, the unboxing, is if you don't have a t variable that accounts for different time periods for each cell or subject, or if you have a different time for each count, which we'll get into in the next couple of sets of slides what I'm talking about, then the form is given here. So where you're actually looking at the expected count divided by some value t for different rates and for different time periods of exposure for each subject or cell. And the reason for using the log link is that counts are in the range of 0 to infinity. And the log transforms that to the real range of negative infinity to infinity. And so lambda I, the Poisson parameter, is the rate of occurrence of the outcome, or if you don't have a time variable that you're dividing by, that would just be the average count. And then the log link is the link for Poisson GLM. And using the log link gives a rate ratio interpretation. And like we did with binary data in previous weeks, other link functions could be used in principle, but the log link is best and was normally used, and that is because it gives the appropriate range for linking the count data with the linear predictor. And it also has this nice rate ratio interpretation. And I'll get into all of more of this in the next couple sets of slides. Okay, so if you have count yi and exposure time ti, a Poisson GLM takes the form below, where you have log lambda is equal to the xi transpose beta. Or we could equivalently take this exposure time t and bring it over to the right side to get this form given here. And the way that I did that is I say I have log of the expected value of yi given x over the exposure ti, and that's equal to xi transpose beta. Well, I can separate out log expectation yi given xi minus log ti. And then I can bring that log exposure over to the right-hand side to get log of the expectation of yi given xi equals xi transpose beta plus log of ti. And that's just how I went from this first equation here and then got to the second equation. And the reason I'm doing this is because though we conceptualize our data in terms of rates, which is the count divided by the exposure time, in practice, when we actually model this, we model it with what's called an offset term, which is this term here, and we model it in this form. And that should become more clear in the next couple slides as well, if it's not clear now. So in general, how do we interpret betas that for continuous covariates in a Poisson regression model? Well, let's take a general Poisson model with a single covariate and where that xi covariate is continuous. The form of the model will look like this. The beta 0 is the log of the rate of the occurrence of the outcome for someone with values of xi equals 0. And the beta 1 is the log of the ratio of rates associated with a 1 unit increase in xi. And then exponentiated regression coefficients are rate ratios. If instead you have a binary covariate, let's say now that xi is a binary treatment variable where xi equals 1 for the ith subject, if the ith subject received treatment, and xi equals 0 if placebo, the model is written the same way. And now we would have a slightly different interpretation of the betas for that binary covariate, where the intercept beta 0 would be the log of the rate of the occurrence of the outcome for subjects who received placebo, and beta 1 would be the log of the ratio of the rate in treated subjects compared to the rate in placebo subjects. So inference and estimation of your betas, we get that the same way that we did for logistic regression, where you start with the PDF. In this case, we have f of y for parameter lambda is the PMF of the Poisson distribution. And then based on that PMF, you calculate your likelihood function by multiplying together the PMFs. And you do that. When doing that, you get this expression for the likelihood given below. And then to actually get estimates for your betas in this modeling framework, you would take the maximum, you would use maximum likelihood estimation to get the MLEs of the betas using this likelihood. And this is fit using the GLM function in R as well. This finds the MLE of the betas to give estimates beta hat. And like we did for logistic regression, we can use Wald and likelihood ratio tests to get inference about our parameters. The interpretation of the betas will be different because now we have rate ratios instead of odds ratios, but in essence, the inference still works the same way. So let's look at an example using the asthma data from the previous lecture. So in this data set, a group of clinicians wishes to study the association between air temperature and physician claims for asthma. In this case, the exposure TI is the same for all cells. It's just the exposure time is 1 month in each cell. So we have a 1 month time frame, so TI equals 1 for every cell. And so implicitly, this means the rate that we're modeling is asthma claims, number of asthma claims per month. You can put the data into R using this piece of code. And then we can model the actual Poisson regression using this piece of code here. So we're still using the GLM function. We're looking at the outcome variable number of claims against the covariate of interest, the average air temperature, using a formula the same way. What changes is now instead of family equals binomial, we use family equals Poisson. And so looking at the summary of that model, it looks very much the same as it did before when we were doing logistic regression, where you still have your coefficients and your inference table. And we'll talk more about how to interpret that. But one of the differences here is now where they have this dispersion parameter for Poisson family taken to be one message. And what this means here is that the variance that we're modeling for this is equal to the expected value of the outcome. And that's just one of the assumptions we made about the Poisson, just when we're using the Poisson distribution, where the expected value of y is equal to lambda and variance is equal to lambda as well. And sometimes this is an assumption that's violated, but we'll talk about that in a few lectures. So below, I extract the coefficients and get confidence intervals. So here I'm exponentiating the coefficients to get the rate and the rate ratio. You can also get confidence intervals. This will give you confidence intervals that are Wald confidence intervals, or you can get confidence intervals based on the likelihood ratio statistic. And below I give some interpretations for the beta values, where the beta 0, the intercept term, is the log of the rate of asthma when the average air temperature is 0 degrees. Is this interpretable? Well, in this data set, the minimum value of the average temperature variable is equal to 21. So that's not that close to 0. So the zero air temperature is sort of outside of the range of this data set. So I would say in this case, no, beta 0 is not particularly interpretable. You always have to think about that in the context of your actual problem. And here beta 1 is the log of the ratio of asthma rates associated with a 1 degree increase in average air temperature. And you can also extract the exponentiated confidence intervals, and that's what I've extracted below. We'll go through more examples with more interpretations in the next couple lectures. But in the context of this data, if you did want to interpret the exponentiated intercept, you thought it was interpretable, say we had a range of data that was closer to 0, then you would say that the expected rate of asthma when the air temperature is 0 degrees is about 13.5 cases per month. And the interpretation of the beta 1 is the expected change in rate ratio associated with a 1 degree increase in average air temperature. For example, the expected rate of asthma when air temperature is 33 degrees is 0.995 times the expected rate of asthma when the air temperature is 32 degrees. And another way to express the rate ratio is as a percent increase or decrease instead. And you do this by subtracting the rate ratio from 1 and multiplying by 100. And here we would say that each 1 degree increase in average air temperature is associated with a 0.5% decrease in asthma claims. This is a very small change in the rate ratio. So what we could do is we could change the units to look at differences in 10 degrees instead. And we do this by multiplying the coefficients by 10 and then exponentiating. Which gives you a rate ratio value of 0.948. And then we would say that the expected rate of asthma when air temperature is 32 degrees is 0.948 times the expected rate of asthma when air temperature is 22 degrees. Or each 10 degree increase in average air temperature is associated with a 5.2% decrease in asthma claims. Like we did for logistic regression, we can also use a deviance chi-squared statistic to test goodness of fit for Poisson regression models. And I'll go through an example of this in lab in more detail, but to cover some of the confusion that we had from the logistic regression goodness of fit test. But the way that this generally works is that you compare the saturated model to the model of interest, just like we did for logistic regression. And the maximum number of parameters for the saturated model is the same as the number of cells in the table. So what's the number of parameters in the saturated model for the asthma data? Well, the way that this data looks, each cell is 1 month of the year. And in this data set, we actually don't have all 12 months. We only have data on 10 months of the year. So there are 10 possible months, means the maximum number of cells in the table is 10. The maximum number of parameters is 10, so that's the number of parameters in the saturated model. In general, how would we know if a model is a saturated? And so in order to, going back to that, so we model the saturated model by looking at the number of claims against month. That will model every single cell in this data set. And so how do we know that that model that we defined in the previous slide is the saturated model? Well, you'll know if something is a saturated model is if you look at the residual degrees of freedom, which is something that's returned by the GLM object. You can get it by doing $df.residual. So if if that's equal to 0, that means that the saturated model has 0 degree. That means that the model that you're working with has 0 degrees of freedom. And the saturated model has 0 degrees of freedom. So this will tell you that you're working with the saturated model. And again, I'll cover this in more detail in one of the labs. So in lecture 4.4, we talked about the deviance chi-squared statistic, which comes from a ratio of the likelihood under your model of interest to the likelihood of the saturated model. And we calculated this by calculating the actual ratio of log likelihoods in lecture 4.4. However, you don't need to calculate it that way because the test statistic of interest is actually returned in R as part of the GLM summary. You need to know, however, when it's actually appropriate to use this statistic. So anytime for your model of interest, you can actually extract the deviance and the residual degrees of freedom, then calculate a p-value using the p chi-squared function. So you don't actually have to run the saturated model. So you get the test statistic by accessing the deviance from your model object, and that compares. And then you get the degrees of freedom by looking at the residual degrees of freedom. This is the difference in the number of parameters between your model of interest and the saturated model. And then you can use this test statistic and the degrees of freedom to calculate a p-value using the chi-squared distribution, because this test statistic will follow a chi-squared distribution asymptotically. And that will give you a p-value for the goodness of fit test. And in this case, we have a p-value that's marginally significant, and we'd reject the null hypothesis that our model fits the data. So we might want to seek a better fitting model. So what would be a better model in this case? Well, the relationship between average temperature and asthma claims per month appears nonlinear. Plot it to see for yourself. So let's try adding a quadratic term. And we can add a quadratic term in the model statement by adding this part of the code here. And then that just adds a squared version of your temperature term to your model. Here's a summary of the coefficients. Both the temperature term and the squared temperature term are significant. But of course, quadratic terms are always going to be harder to interpret. But let's plot it to see if the fit looks better. So plotting our results here, we see the model values. We see our linear fit for air temperature, and then we see a quadratic fit as well. And in this case, the quadratic fit does appear to fit the data better. However, we don't have a lot of points in this data set, so we would need more data to properly evaluate this. So this was just one example, and in the next lecture, I'm going to go through several more examples of Poisson regression in R.